activity series. Yes, there's many activities that will be coming up. Okay, so we're not gonna go play dodgeball. Okay, although that kind of would be nice to like see how atoms can kind of work together. Okay, so an activity series is actually something that's gonna help explain the reactivity patterns of substances which help us predict how bonding is likely to happen. Okay? So this whole time we've just been assuming like you make a positive charge and a negative charge and that's going to form an ionic compound. And then if we have a nonmetal and a nonmetal, we just know that that's going to make a molecular compound. But this whole entire time, why is it that those particular ones tend to be attracted to each other has never been really explained. Okay, so the beginning kind of stages here is just to talk about how is it that certain things are super reactive versus things are not reactive. Okay, so what do we know about our metals? Who's the most reactive group of metals there? Group 1, okay? So why is it? Okay, we'll kind of go into that anyways eventually. Okay, and then in terms of the nonmetals, who's the most reactive there? The halogens, right? We've been talking about it forever and ever that these halogens are very reactive, but yet noble gases are not. Okay, so that's what we're going to go into for here. Okay, so if everybody could grab their periodic table, there's actually a few trends that we want to take a look at. Okay. So group 1 to group 17 elements, okay? The further you travel out from the middle of the table, the more reactive it's going to be. So, if you look at your periodic table, okay, if you start in the middle, this is where the least reactive type of substances are, okay? And as you travel more to the outside towards group 2, 1, okay, that's how metals tend to get more reactive. If you travel more from the middle of the table to the right, okay, to the right, and as you go towards group 17, the more reactive your elements are actually going to be. So that's one of the trends that we actually see from this periodic table, okay? So don't forget that Mendeleev as well was kind of predicting where things should slot into, even though they kind of only started off with a few elements to put into this pattern. But otherwise, as things kind of started getting discovered and the different elements started getting discovered, there are actual perfect patterns that get formed in here, okay? So if we move from the middle of the table to the outside, the more reactive you're going to be, okay? So draw like a little diagram here too. Okay, so there's your little pseudo table, like that. Okay, so the more to the outside, the more reactive you're going to be. Okay, so more reactive is the one at the top. Okay, so that's the first little rule for reactivity. Yeah, to the outsides you go more reactive. Obviously group 18 is kind of a funny one because it's noble gas and they're not reactive. Okay. Okay, so the next trend as well that we see is in representative elements. So representative elements, what do we mean by that? Who remembers? Numbers 1 to 20 only, okay? So for number 1 to 20, and that's why we kind of said that the Bohr model is like really easy to explain until you get to that super huge schwack load of elements that are found in the transitions. Kind of gets a little bit more complicated at that point, but if we talk about only elements numbers 1 to 20, the larger you are, the more reactive you are. Okay, so larger elements will tend to be more reactive, and then smaller elements tend to be less reactive. Okay, now one of the explanations for that as well is just simply by the size of like the nucleus and how many valence electrons you might have. The more that you have out there in these energy levels, the more likely it's going to be easy to steal electrons or give electrons and things like that. So the larger your energy levels kind of are, and the more electrons that you have, it's a lot harder for an atom, let's say, to kind of keep track of them. So in that case, it's really easy for us to kind of like manipulate those electrons that we're going to be dealing with for bonding purposes to make these other compounds. Okay, so if we were to kind of look at it this way, so back into our little diagram, okay, our representative elements start off with hydrogen. Whoops. Okay, hydrogen tends to be least reactive in a way, okay, according to this. So as we were traveling to the right and then kind of keep that continuity going, the more reactive these are going to actually be.
What about like the Hindenburg film? That was pretty reactive.
Well, hydrogen gas.
Hydrogen bomb.
Hydrogen gas is funny in its own way. That's why it's got a weird different color in your guys' periodic table. Okay, now, speaking to that, that's a good comment. The nonmetals, okay, which hydrogen actually is, okay, and hydrogen is actually the smallest atom that's out there, okay. Nonmetals actually follow a slightly different rule, okay. So nonmetals, oh, we're gonna fall off here. Okay, so nonmetals, what they actually do is that your reactivity actually increases the smaller that you actually are. Okay, so smaller elements of only nonmetals, okay, are going to be more reactive than larger elements in the periodic table of the nonmetal section. Okay, so hydrogen, very reactive. However, hydrogen is actually not our most reactive of those because they kind of fall into the pattern of like the representative elements, and they kind of have that group, the group 1 and 17 and the very extreme ends of it. So hydrogen's always kind of in its own little world. However, if you look at the nonmetals, one of the smaller nonmetals, and in conjunction with having your group 17 and more to the outside, who should be your most reactive nonmetal? It's fluorine. It's always fluorine, okay? So in that case, you kind of have to combine some of these rules for the fact that the smaller that you are, the more reactive you are if you're a nonmetal, but then you can kind of make predictions as how reactive something's going to be based on its location in the periodic table, okay? So on that note, what this means of the nonmetal, okay? Fluorine is the most reactive. Okay, so everybody probably wants to memorize that, okay? How that falls into play is the fact that the nonmetal is going to follow the rule of how small it is, but also from moving from the middle of the periodic table to the far right, you're also going to get that trend of more reactivity. So in that case there, the more to the outside that we go, fluorine happens to be our most reactive nonmetal. Okay? Sound good? All right. Now, our most reactive metal. If you follow the rules, okay? So if you go just regular elements, okay, and this actually does work with like the representative elements in a sense as well. Okay, so if we move from the middle of the table, our more reactive stuff is always in group 1. That's just one of the rules that we kind of see, or one of the patterns that we see inside of our activity series. Okay, but on top of that, who's our largest metal in that sense? It's francium, okay? So francium is the most reactive metal that we actually have out there, okay? So between all of these little kind of trends, there's other stuff that obviously comes into play with it. This is the tendency and the pattern of what we see inside of how reactive things are, okay?